All right, so we're looking at the second part of 0.5. So on Friday, our focus was on inverses. We focused on finding the inverse. We understand that inverses flip-flop their domain and range. So, and we understood that in order to beat inverses, the function had to be 1-to-1, which meant it passed the vertical and horizontal line test. Today, we're going to talk about logarithms, and logarithms have inverses. Their inverses are also unique, and we're going to talk about the uniqueness of these logs and their inverses. So a base A logarithm function says that if A is a positive real number other than 1, the base A exponential function f of x equals a to the x is 1-to-1. The minute we know a function is 1-to-1, we know it has an inverse. And in this case, we call the inverse of that a logarithm of base A. So what that means is its inverse is the log function. So like a log base A. So the original is y equals a to the x. Its inverse is log base A. X equals y. The base of a logarithm function, y equals log base A of x, is the inverse of the exponential function, y equals a of x. That's why you can flip the two and use them interchangeably. So sometimes we take a log base A and we rewrite it as a function a to the x so we can solve for y. The domain of a log is 0 to infinity. The domain of a log is 0 to infinity. That means you can never take the log of a negative x value. You can never take the log of a negative x value. And its range is all reals. So this is a little bit different from what we're used to. So really what that's saying is a to the x is the original function whose domain is all reals and whose range is 0 to infinity. The logarithm function with base e and base 10 are so important that they have special keys on your calculator. So that's the log base e, which is the natural log on your calculator. And then the log key on your calculator is a log base 10. So if you look on your graphing calculator on that home screen, you have a natural log key. That's technically the log of e. And you just have a log key. That's a log base 10. And a to a log base a of x is equal to x. That's the identity. And e to the natural log of x is equal to x. That's also the identity. You can also say the natural log of e to the x is equal to x. So we know that we like to do function composition to get to the identity. That's what we're taking into example here. That's like saying f of x equals e to the x. Its inverse, f inverse x, equals the natural log of x. And if you take f of f inverse of x, that's like taking f of ln x, which is like saying e to the ln of x, which equals x. So again, this is from Friday. That's function composition. To prove two functions are inverses, they have to equal the identity. So we have two functions are inverses, their function composition is equal to x. So one of the things we're going to focus on is being able to rewrite logarithms as well as trig functions. So that's what we're going to look at today. We're going to look at rewriting logarithms as well as trig functions. So in this example here, you have log base a of xy equals log base a of x plus log base a of y. The quotient rule says log base a of x divides y is the same as log base a of x minus log base a of y. So if any logs have the same basis and they're being added, that's the same as multiplying. If they're being subtracted, that's the same as dividing. And if it's a power to a power, then that power can come out in front. So what we're going to do now is apply these properties to some examples. We have one last property though to talk about before we do that application, and that property is the change of base. Your new calculators now, you can do a log of any base, but in the past you could not. So we had to use what we call the change of base formula. And what that is it's the natural log of the inside over the natural log of the base. So the newer graphing calculators, like I said, they have a log base a of x function in math. Previously, before those graphing calculators had that feature, you had to type it in like this. So real quick, I'll show you where that feature is. So again, if you go to your graphing calculators and you hit the math key right here, so you're just going to hit math, you can now go down and where it says log base, that allows you to type in a log of any base. So you could do 8 and maybe 6 and you get your answer. So again, you could do any base. So if you made this, let's say a 4 and a 2, you get 2. And if you think about the property of these logs and their bases, what that is saying is that base 2 squared is 4. So base answer becomes squared equals the number inside your base. Previously, you had to use the ln key down here. And you would have to have said the ln of 4 divided by the ln of 2 to get that answer. And you can see it still works, but that was just the old way we had to do it. Okay? So we're going to use our inverse properties to solve. So the first one is the natural log of x equals 3t plus 5. We want to isolate x. So to isolate x, you have to use the inverse properties to get the natural log gone. So in order to do that, we're going to e both sides. And that gives you x equals e to the 3t plus 5. Since we don't know what t is, that's simply our answer. In example number 2, we have e to the 2x equals 10. To solve for x, you're going to ln both sides. The ln and the e cancel each other, leaving 2x equals the natural log of 10. Divide both sides by 2, and we get x equals 1/2 the natural log of 10. And again, we could use a calculator for this problem and get an approximation. So you type 0.5 natural log 10, and we would see that that's approximately 1.151. So this is the actual, this is the approximation. Yes. Not in the beginning, but if it's, probably not. That's something I'd have to go look at. I usually try to give points based off of like AP, like how they would grade you. I don't know if I know that answer, so I have to go look that up. It must not ever be an issue. Like, do you know what I mean? If I say approximate and you put equals, I don't think they're going to dock you. Okay, number 2. So now, this is an a to the y equals x problem. So we can't rewrite 12 to have a base of 2. So when you can't rewrite the one side to have the same base as the other, we use our logs. So this is really the same as saying the log base 2 of x, log base 2 of 12 equals x. And now you could get an approximation on your calculator, and you could solve, or know that this right here represents a number in and of itself. So you'd go to that math, go down to the log base key, type in 2, type in 12, and we get 3.5849. And again, that should make sense because 2 to the 3 is 8. to the 4 is 16. So to be in between 8 and 16, it would have to be 3 point something. You could also do the natural log of 12 divided by the natural log of 2. And you'd see that that also gives you that same value of 3.5849. So again, approximation versus actual. Solve the following for x. You have e to the x plus 5 equals 60. In order to ln both sides, you need to isolate the e to the x. So we're going to first subtract 5 from both sides. So I get e to the x equals 55. Then we're going to ln both sides. And we get x equals the natural log of 55. Which again is approximately 4.007. We can also look at population growth problems. Population growth is where you have a function that's growing exponentially. So in this case, we have the population of a city. The city population is growing at the given rate. So T represents the year 1990. According to the model, when will the population reach 150? So this right here, that's going to represent P. So we'd say 150,000 equals 105,300 e to the 0.015 t. Now it would just depend. If this were a calculator problem, then I would tell you to put this in y1 and this in y2 and find their intersection to save you time. If it was a non-calculator problem or a multiple choice, then you would have to solve it by hand. So you take 105,300 and divide it. So you'd get 1500 over 1053. That would equal e to the 0.015 t. We know to get rid of the e, we're going to ln both sides. So that gives the natural log of 1500 over 1053 equals 0.015 t. You divide both sides by 0.015. So natural log of 1500 over 1053 divided by 0.015 is 23.588, which means that the population will be 150,023 years after 1990. So you would have to take that value and add it to 1990. And then your explanation would be in 2013. the population will reach 150,000. Good. Okay, that's going to be your textbook problems. And then we're going to look at a little bit of, like I said, trig stuff today.